Welcome to physics for January the 25th. As usual, before we get into the new material, let's talk about some announcements. First off, the chest rework was due last Saturday at midnight, and most of you got it in. Most of you did well. A few of you did not. And I hope you realize that that chest rework counts for like over 50 points, whereas a regular homework assignment is only 10. So that one assignment is worth as much as 5 regular homework assignments. If you didn't turn it in, for sure, go back and do it. Now it's going to cost you a late pass, but it's a new term now. So everybody, you get your 2 late passes back at the beginning of every term. So you all have 2 late passes. This is definitely one to use, if you could pick and choose which ones you want to use your late passes on, this is definitely one you want to use your late pass on. So get it in. Also, the lab reports. I have looked over the lab reports and graded them, and I posted the rubric on Canvas. So you should be able to see exactly why you got what you got. But I'd like to take a few minutes and talk about some of the things. I've had people ask me, they say, well, Mr. Hendricks, I thought that I did everything you asked, but you didn't give me the highest possible. You only get, you didn't give me a very good, you only gave me a good. So what do I have to do in order to get a very good? Well, okay, let me give you a couple examples. I think it's worth spending a little bit of time. Writing good lab reports is really important. You guys need to know how to properly plan and execute a lab, and you need to know how to write a good report afterwards. So what I've done is I've cut and pasted a couple examples that I thought were especially good. All right, so every lab report should start out with a sentence or two that describes what is the purpose of the lab. So what you see here are 3 examples that I gave the highest points to. And I want you to know what they did that the rest of you did not do that earned them the highest points. So let's look at this first one here. Okay, so the purpose of this lab is to transition from the study of classical mechanics to wave mechanics by studying the motion of the pendulum and see how the string affects it. You see, the transition from the study of classical mechanics to wave mechanics. That's what I was hoping you guys would pick up on. I mean, so many of you said, well, the purpose of this lab was to learn how a pendulum works. Well, yeah, but there's a deeper purpose. When I assign a lab, I usually always have the superficial goal, which in this case is learn how a pendulum works, but then I have a much deeper, broader, more important goal. And so in this case, that deeper, broader, more important goal is to show you the connection between classical mechanics and wave mechanics. And so if you want to get the highest score possible, you need to talk about the deeper purpose. And this one here, basically the same thing to ease the transition from classical to wave mechanics. This bottom one, they took a slightly different approach, but I thought that was good. They said that not only were we trying to learn about how pendulums work, but we also wanted to make sure that we know how to use regressions to find equations that fit the data. I thought that was good because yes, that was a very important part of the lab, because what I've learned is that so many students, they get to this point in their math careers, their high school years, and if I ask them to do a regression, they look at me and say, huh, what's a regression? You guys need to know how to do regressions. That's really important. So this is the kind of stuff I was looking for if you wanted to get the highest possible on the grade, talking about the purpose of the lab. Now, as far as the pictures go, some of you put a lot of time and effort into doing a really good computer generated drawing, and others of you just did hand sketches. And I accept both, and I would give full credit. A hand sketch that's really well done, I would give that just as many points as somebody who spent all the time making a really pretty looking box and all that. I don't want you to spend lots of time doing fancy computer graphics. Now, some of you are really good at computer graphics and you can do them very quickly. So if that's the case, then by all means. But a hand-drawn sketch is okay. I'm fine with that. Now, I do like to see a little bit more information there. Like, for instance, this hand-drawn sketch here, maybe maybe I wouldn't really give that one the full credit. Whereas this one over here, you see how the one on the right here, it tells you what is L. L is the distance from here to here. That's good. That's the kind of thing I like to see. And what is theta? Theta is this angle. And this is the equilibrium position. Here's the maximum position. This is the kind of stuff that I like. This one right here, this is my favorite out of all the drawings, because it not only shows you a pendulum, but it also shows you, well, L is measured from here to here, and the equilibrium position is here. That's kind of stuff I want to see in your drawings. This is a good one. Okay, now, when it came to the description, so many of you did not go into detail talking about what you did, and especially why you did it. That's the part that so many of you left out. Why did you do things the way that you did? So here is an example that I thought was pretty good, where they talked about why they did what they did. Okay, so they said, okay, there's many options for how to fix the pendulum, right? You could hold it with your hand, but this would cause issues because it's impossible to hold your hand still, right? Okay, so another thing is you could attach it to the underside of some structure, which is the option they chose. So they hung it from the bunk bed. So you see that they're not only telling me what they did, but they're telling me why they did it that way. They're telling me these are the other options that I considered, but I rejected them for this reason right here. This is the kind of thing that I'm looking for in the data, or in the explanation. This is what I want. Also, you'll notice here that they talked about make sure that you hold the pendulum at an angle that is less than 15 degrees, because otherwise you find out that the angle does affect the period of the pendulum, right? But as long as you keep it less than 15, you're okay. And then also they said, make sure that you measure 10 periods before you stop the timer, because otherwise human error is going to be a problem because of human reaction time. So we want to average over time over 10 times. This is the kind of detail that I want everybody to go into. Tell me what you did in detail and tell me why you did it that way. This is what I'm looking for. Okay, now with the data, a lot of you just gave me the data right straight from Desmos, just did a screenshot on Desmos. This, what you see right here, this is more what I'm looking for. I want to see not just the average, but I want to see what did you get for each of the 3 tries that you did, that how repeatable are your results. So like, if I look here, I see that for 30 centimeters you got a period of this, but I want to know how repeatable those results are. I want to know how much variation did you get. And the only way I can see that is if you give me all of your data, not just the average, but all the other data too. So please, in the future, please do it like that. Okay, this was an interesting one where the person who did this report, they thought that the data they had wasn't really good for 2 sig figs, but they included 2 sig figs anyway, because otherwise you wouldn't have enough information. Well, I wonder why they said that, because when you measured this length right here, you should have been able to measure it to an accuracy of plus or minus better than 1 sig fig. I mean, if you wanted the length to be 0.1 meters, which by the way is 10 centimeters, right? You should know that it's within somewhere between 9 and 11. So you should be able to give me 1 extra sig fig. You should be able to tell me that this length here was 0.10 and 0.210. I don't know why this person didn't think that they could measure the length to within 2 sig figs. I think you could. But I was glad that they went ahead and did 2 sig figs and the rest of it, because otherwise, I mean, they're right in saying it would have been meaningless if they'd only given 1 sig fig. Okay, so now here, we need to talk a lot about this. So many of you guys ended up using a quadratic or a cubic. And a lot of it was based on the R squared value. So like, for instance, in this case right here, the person said that they had an R squared of 0.998, which was really good. And when they went to the when they went to the cubic, it was better. It was maybe slightly better, but not really. It was mostly tied. So they went with a quadratic, so it was simpler. Okay, so I like that. But if you look at this quadratic, you'll see that the coefficient of the L squared is negative. That means if we continue this guy out, it's going to look like this. So I'll admit, yeah, over that limited range that we did, that fits it really well. But if you were to extend that out, if you go to 2 meters or 3 meters or 4 meters or 5 meters, according to the predictions of this quadratic equation, what's going to happen is you're going to reach a maximum period. And then as you go even longer, the period is going to get shorter and shorter and shorter again. Is that really going to happen? I mean, I would hope that you guys realize that, yeah, that's not the way it's going to work. I mean, the longer the period is, or the longer the length of the string is, the longer the period is going to be. You're not going to reach some maximum, and then it turns around and starts getting shorter again. So even though the quadratic and the cubic fit really well over this limited range that we had, I would hope that you guys would look out beyond that. So like here's a case where you can see with they used a cubic here to fit it. And I would hope that you realize something funny here happens because it starts off steep and then it gets less steep. And then it reaches what we call an inflection point where it starts getting steeper again. Why would that happen? What is it? What is physically going on that would cause there to be an inflection point like that? That I would hope that you'd realize that, yeah, that doesn't make sense. Here's one where you can see it even more clearly, that definite inflection point there. The square root function, this is the one that fits the best, because the square root function, even if you continue out past 1 meter, the square root function isn't going to do any weird things. There's not going to be a weird inflection. It's not going to turn around and start going downward. So I would hope that you'd realize the square root function is really the only one of the ones that we consider that makes sense. Here's a cubic one where, according to this, you can see it goes really bad, really fast. In fact, even before it gets to 1 meter here, you know, according to the predictions of this equation, it turns around when you get to about 0.6 meters. So this person, they didn't give me all the data that it went on. I wanted you to go all the way to 1 meter. And if they'd gone to 1 meter, they would see that there's no way that the period goes back down again. Okay, so I had to dock some points here. Let's see, what else have we got here? A cubic one, clearly there's no way that the cubic one, or I'm sorry, the quadratic one here that you see, no way that can be the right one. Now here, the person who did this one, they bunched all of their data really closely together. So it's hard to see, whoops, sorry. Let me turn on annotation before I touch my screen here. The data is grouped too closely together. Everything from here on up is just wasted space. Everything from here on down is just wasted space. So what you should do is you should expand your Y window so that you can see this much better. And here's another one that's even, this is an even extreme case. I mean, look how closely those data points are packed together. You can't tell anything. This graph is zoomed out way too much. You can't tell how well those data points fit the curve. And you got all this wasted space over here, all this over here is wasted, everything down here is wasted, everything up here is wasted. Zoom in, guys. Do not give me a graph that looks like this. You need to zoom in so that I can see what's happening there. Okay, this one's just a minor point here, but still it's worth noting. So what happened was they had a section here where they were giving me the results, and now they want to start a new section. So they have a section header, but the section header is at the bottom of the page, and then the section that it's the header for is over on the next page. So we have a word for this. We call this an orphan header because it's all by itself. The thing that it's heading is on a completely different page. Don't do orphan headers like that. Okay, if this happens, put in a page break so that the section header is located on the same page as the section that is the header for, please. Don't give me orphan headers like that. Okay, So that's pretty much it for the feedback on the lab reports. If you didn't do the lab report, well, use up a late pass. Because again, lab reports are worth a lot more than regular homework assignments are worth. So are there any questions about the feedback on the lab reports? Okay, not hearing any, not seeing any. All right, well, let's talk about last night's homework. So here are the answers, the ones you didn't look up. So some of these obviously are ones that I want to discuss with you. So we'll do that in a minute. But first, let's do what we always do. If you could only see one problem worked through, please type in the chat box telling me what problem you would want to see. And hopefully we'll do more than one, but we might not have time. Okay, problem number 20. Seeing a lot of votes for number 20. Okay, well, all right. Looks like everybody's in agreement. 20 is the one you want. Okay, let's see what we got here. Okay, so pulses are generated at a certain speed. Okay, find what is the speed of the wave. Okay. All right, this one shouldn't be too difficult. Let's open up a whiteboard. Okay, so let's see what they tell us. They're telling us that we get 5 pulses every 0.1 seconds. Okay, so what are they telling us there? Is that the period? Is that the frequency? Is that the wavelength? Is that the shoe size? What information have they just told us when they say we got 5 pulses for every 1.1 seconds? Frequency. What they've told us is the frequency, because what is the definition of frequency? You need to know this. Frequency is defined as the number of things that happen. In this case, the thing is the pulses. The number of things that happen per second, okay? Or is in this case, per the number of seconds, all right? So when they tell us that we get 5 pulses every 0.1 seconds, so that's 5 pulses every 0.1 seconds. And notice I did not write pulses because the thing that goes up here is, oops, okay. So I didn't write pulses. The thing that goes up there, I want units. And if I'm counting things, well, I don't really have units. I mean, I just want to know how many of those things there are. So if I say 5 pulses, like, that's not 5 meters, that's 5 seconds. It's just 5 without a unit. Okay. So if I take 5 divided by 0.1, so that gives me 50 pulses per second. So my units here are 1/seconds. So 50 times per second is that there's 50 pulses will go by in 1 second. If 5 pulses go by in 1/10 of a second, that means 50 pulses are going to go by in 1 second. So that means that my frequency is 50, whatever units it is we use to measure frequency, which, as you can see here, is 1/seconds, which is normally called hertz. And it's abbreviated with an HZ, capital H, lowercase z. Okay, so 50 hertz is the same thing as saying 50 times per second, 50 counts of whatever it is you're counting, 50 of them per second. So a hertz is the same thing as a 1/seconds. All right, so what they've told us then is the frequency. So we now know the frequency equals 50 hertz. And let's see what else they tell us. They tell us that the wavelength is 1.20 centimeters. Now, hopefully you guys realize that centimeters is not a standard physics unit. So if you got a different answer than I got, maybe this is the reason, because we need to work in standard physics units. So we shouldn't write it as 1.2 centimeters. We should write it as 0.012 meters. That is the number that we use for lambda. Okay, so now we're trying to find out what is V. So we just take the equation which we derived last time. And let me tell you a secret here, guys. I do not have that equation memorized. Now, I realize some of you are going to say, wait a minute, Mr. Hendricks, you're a physics teacher. How is it that you could possibly not have such an important equation memorized? Well, I don't have it memorized because I don't need to have it memorized. I can rederive it in no time flat, okay? So remember we started with distance equals rate times time. So if you got a wave moving at speed v, okay, so that's an r there. Okay, so the wave is moving at speed v. So if it moves a distance that's equal to the wavelength, then the amount of time that it took to do that is by definition the period. And the period is defined to be 1 over the frequency. So if I replace that for that, so lambda equals v over f, there we are. That is the most important equation for the rest of the year. You are going to be using this equation so much in between now and May that maybe you should go ahead and memorize it, or you can be like me, just rederive it every time you need. Okay, so we know what lambda is, we know what f is, we're looking for the velocity. So let's multiply both sides by f. So velocity then equals f times lambda. So f is 50 hertz, lambda is 0.12 meters. So when you punch out those numbers, then you should get 0.6 as your answer. So if you didn't get 0.6, probably because you used centimeters instead of meters. All right, is that okay for question number 20? You guys comfortable with that now? All right, not hearing anything, not seeing anything. All right, now problem number 22, I wanted to discuss briefly. 22 says that you've got what they call a coil spring toy. I don't know why they don't just come out and call it a slinky. I mean, that's what they mean. Maybe they're worried that the people who make slinky are going to sue them if they use their trademark. But basically, you got a slinky, right? Okay. So imagine, pretend, actually, okay. Now this is a stiff spring, so it's not a slinky. A slinky is a really not stiff. Okay. All right. So if I pull on the slinky here, eventually that pulse is going to reach the other side, but it's going to take a little bit of time for the pulse to go from here to there. It doesn't travel instantly. Now, the stiffer the spring is, the faster it goes. And in fact, if I have just let's say I have a bar, I have a solid bar here. You might not realize it, but this solid bar is actually like a slinky. It's just a super, super stiff slinky. There is actually space in between all the molecules here. So if I tap on this end of the bar, you might think that that tap is instantly transferred over from my right hand to my left hand, but in fact, it's not. It's exactly the same as if I had a slinky and I tap on the slinky. When I tap here, it's going to create a pulse, and that pulse takes a little bit of time to travel through there, even in a supposedly solid object, because there's no such thing as a really truly solid object. There's actually space in between the molecules there. Now, with an object that we refer to as solid, they're packed together so tightly that it feels like it instantaneously gets transferred, but it actually doesn't. Okay. All right, let's see, what was the other one I wanted to talk about? 24. Okay, so on 24, we're talking about the fact that when I have a wave, so I've got a string here. So if I shake my right hand, what happens is I create a wave and that pulse travels over here, and eventually my left hand will feel it. So if I give an upward pull here, what I'm doing is I'm putting energy into the wave, and then that energy travels up the other side, and then my right hand eventually feels the pull and it gets yanked up from the pole. So I have transferred energy from one hand to the other hand. And the medium that carried that energy was the string. Or if it's a sound wave, the medium is air. Or if it's some other wave, the medium is, water or whatever. Okay, the medium carries the energy, but the medium doesn't move. Let's say I have a knot. Okay, so there's a knot tied in the string. So when I get this wave going like that, okay, now the knot does move up and down, but when the wave pulse has passed, that knot is right back in the same place where it was before. So I can transfer energy from one hand to the other hand, but not matter. Okay, only energy moves. The string ends up in the same place as starting, and after the wave pulse has passed, it's there. So we transferred energy without transferring matter. That's what waves do. Okay, now the last thing on my sheet here is the canvas problem. So I want to make sure that we do that. All right, so let's go into Canvas. Here it is. Let's open up, find out what the problem was. Okay, so we want to duplicate this. We want to come up with an equation that duplicates this. All right, so we need to know what is the amplitude. We need to know what is the period. Okay, so hopefully you guys realize that the amplitude is not the distance from the lowest to the highest. Okay, a lot of people think that it's not. Amplitude is the distance from the midpoint to the highest. Or if you want, you could say the midpoint to the lowest because it's symmetrical. So if this is 5 and this is 7.1, so our amplitude is 2.1. Okay, and then the period. Well, if we started off here and went down to the bottom and then came back up again, so however much time it took to do that, that's our period. So the period is 2.8 seconds. Okay, so knowing that, then we can go in and we can go to Desmos and create the graph. Oh, and also the offset. We need to know what is the offset. So when I say offset, what I mean is the center point here, how high above the ground is that? So that's 5. All right, so now we can go into Desmos. I'm going to create a new graph. Go to the graphing calculator. All right, so hopefully you guys remember that the generic equation here is y equals a times either the sine or cosine, depending on which one is appropriate for your circumstance, times b t plus c. All right, so we need to figure out whether we want to use sine or cosine. Hopefully you guys know that the amplitude is a, and b is the number that controls the period, but b is not equal to the period. Now for the amplitude it is. The a controls the amplitude, and in fact, a is the number that the amplitude is. B controls the period, but b is not the period. B is 2 pi divided by the period. And then c is just the y offset. All right, so let's try sine, and let's see if sine is going to do the job that we want. Okay, so I'm going to do y equals a, which is 2.1, times the sine of b, which is 2 pi over the period. So 2 times pi divided by the period, which was 2.8. Okay, so that gives me 2.24 times t, times x, because Desmos likes it better if the independent variable is always x. All right, so now I've got something that's looking good, and then I need to do plus 5. Okay, and let me clear out, I've got all my annotations here. Let me erase all my annotations. Okay, so it looks to me like we're getting pretty much what we want. I wish it wouldn't count in 2s. I wanted to count by 1s. So let's have it count by 1s here. Okay, yeah, that makes it a whole lot easier to figure out what's going on here. So yep, you can see our average is at 5. Our highest one is 7.1, our lowest is 2.9. The period there is 2.8. So let me turn back on annotation for a second here. Okay, so if I go from there to there, yeah, that looks like about 2.8. Yep. Okay, so we're good. All right, so the only thing that is wrong is what we call the phase. The phase is the left and right shift. So if you look here, what we want is we want the thing to start at t equals 0. We want the thing to be at the highest point possible. So at t equals 0, it's up at the highest point. And if you look at our graph here, you'll see that that is not what we have. What we have is that at t equals 0, the thing is at the equilibrium and it's heading upwards. So you can see here that the sign is not the right one to use to match this. Okay, so what we do then is we say, okay, no problem. Instead of doing the sine here, let's make it be the cosine. And yep, now you see, now we're good. So now we can see at t equals 0, it is at the highest, and then it goes down and then it comes back. And also you can see now it's a lot easier to see that it does return to the highest point at 2.8, which is what we wanted. Okay, so for part A, we're good. This is the equation that does it for part A. But we also wanted to do some phase shifting here. So in part B, it says, what if instead of starting the clock when we did at A, we want it so that it's passing through the equilibrium, moving in the positive direction? Well, that was what we started out with. So that would be the sine. So if we go back here, okay, so sine function, yep, there we go. Okay, so this is the answer for part B. So notice that all of the numbers that we have in here are the same as before. Okay, the A value is the same, the B value is the same, the C value is the same. The only thing is we're swapping sine for cosine because we wanted to start here and head upwards rather than what we did before. Okay, so this is all well and good. What about part C? Part C says that what we want to do is we want to start the clock when the mass is passing through the equilibrium point in the negative direction. Uh-oh, how are we going to do that? I mean, our only choices here are sine and cosine. What we want to do is we want to take this point right here and we want to move it over. So basically we want to take the whole graph. We want to shift the whole graph over by an amount right there that is equal to half of the wavelength. Because remember, if you start right here and you go up and over and then, okay, so that right there is one full wavelength. We only want to shift it by half of a wavelength. Now, this is something that many of you guys have probably not encountered in your math class, but I know that some of you have. So if you want to shift it to the left by half of a wavelength, well, first thing you need to recognize that a wavelength corresponds to 2 pi if you're working in radians, which you should be for this. So if we want to shift it by half of a wavelength, that's going to be, so lambda over 2 is just going to be pi. So what we want to do is we want to shift it by pi. So we're going to do that inside the parenthesis there. So we're either going to add pi or subtract pi. Now, those of you that are in Math 3 honors or higher, you should know right ahead. But let's pretend that we don't know. Let's just say, well, let's just guess. Let's try adding pi. And we see, hey, yeah, that did it. Okay. Whereas if instead of adding pi, if we had subtracted pi, okay, then you can see that well, actually, in this case, that's the nice thing about pi, because pi is half the wavelength. So in this case, you could either add or subtract pi. But if it was pi halves, okay, then you can see it makes a difference. So I don't want to take the time to go into knowing when to add or when to subtract. So what I would say is just go ahead and just for you guys, you can just experiment with it. But basically, if we put in a plus or minus pi inside the parenthesis there, that is called a phase shift. So what it means is it takes the same graph and it just moves the graph either to the right or to the left by a certain amount. So we've changed the phase of the graph. Nothing else changed. The amplitude's still the same, the period's still the same, the y offset's still the same. All we did was we moved it to the right or to the left. So we call that a phase shift. Now, if you haven't yet reached this point in your math class, don't feel too bad. I'm not going to give you a lot of questions there. Okay, so Taituan is suggesting that you could have just added a negative sign in front of the 2. Yes, Taituan, that would have worked in this case. Very good. That would have worked. Okay, but this is a more advanced topic. And so I do not expect all of you guys to know about phase shifts. I just put that in there for those of you who are in Math 3 honors or higher. So hopefully you'll realize that what you're learning in your math class actually does apply to the real world. Okay, so enough of that. Let's talk about the new material now. So the plan is today we are going to finish up chapter 14. We're going to learn what happens when you have multiple waves that are hitting the same spot at the same time. Very interesting and very important things happen when multiple waves hit the same spot at the same time. Okay, so first off, let's see what happens when a wave hits a boundary. All right, so what we've got here is we got a picture showing an incoming wave. So if you just look at this, so this is just one single pulse. So normally a wave consists of multiple pulses, one after the other, but it's easier to understand what's going on if you just look at one single pulse all by itself. Okay, so let's say it's a guitar string and we plucked the string. And so the pluck is now moving from left to right. And it's going to come here and it's going to hit the wall and it's going to bounce back. And so then what happens to it when it bounces back? Well, it depends on what happens at the wall. It depends on how the wave interacts with the wall. So if you have what's called a fixed boundary condition, what that means is the string is tied to the wall in a way that it cannot move up and down. So when this pulse travels along and then it gets over to here, and then it gets over to here. So what's happening is that the stretched string is trying to pull this part of the rope upwards, but the wall is saying, no, 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 I won't allow you to do that. So what's going to happen then is that the wall pulling on the string is going to pull it downwards. And so when it hits the wall and it travels back in the other direction, the wave pulse that previously had been what I like to call a positive wave pulse because it's up higher than the equilibrium string, well, it's going to go back as a negative wave pulse if it hits a fixed boundary wall. But that's not the only way that we could have done this. What we could have done was we could have had what's called a free boundary wall. And so the way we do that is instead of tying the rope to a nail that is nailed into the wall, what we're going to do is we're going to tie the rope to a ring, and that ring is free to move up and down. So when this pulse comes along here and it gets right here, so the stretched string is trying to pull the ring up, and the ring can in fact go up. And so in that case, the reflected pulse is not going to be inverted. So this case up here, we call this an inverted pulse. And then over here, we just call this one not inverted. And it's actually easier to see if you can see a simulation. And so what I did was I went out and I got a simulation and I put it on Canvas. So if we go into the modules section here on Canvas, you're going to see that there's a really neat thing that I've added in here that wasn't before. This is called an online wave reflection simulator. And I want you guys to play with this. So that's why I put it in here. And so you'll recognize it's one of those PEHT simulations that we did from the beginning of the school year. Okay, so what I'm going to do is I'm going to grab on this wrench with my hand, and I'm going to give it a quick pulse up and down. You see what happened there? So over on the right side, what we have is we have a fixed connection. This is like that brick wall where the rope is tied to the nail. So when this pulse comes along, it tries to pull it up, but that fixed connection there is going to say, nope, I'm not going to let it go up. So the reflected pulse in that case, the reflected pulse is inverted. So let's do one more real quick one. There we go. Boom. You see that? The reflected pulse is inverted. All right. What if we switched over here to the loose thing? Okay. So now we got the ring on there. So now let's see what happens when I give it a quick pulse. And there, you see that? The reflected pulse is not inverted that time. Do it again. Aha. Okay, so now some of you might say, okay, great, but really is this useful or is this just trivia? Turns out this is very important for things that we're going to be doing a little bit later. When we talk about light waves and light as it travels through a window glass or travels through the lens on a telescope, it is vitally important to know whether the light that's reflected from the surface, whether it's inverted or whether it's not inverted, it makes a huge difference. So this is not just useless trivia. Okay, you need to know sometimes the wave pulse is not inverted, and sometimes the wave pulse is inverted. And you need to know when. Okay. So there's another important instance that you guys need to know about. And that is what happens when a wave comes to a boundary where you're going from one medium into another medium. Now, here's the word medium. Make sure that you understand what I mean here. When a physicist says the word medium, okay, we are not talking about shirt sizes where we're trying to decide whether to buy a small, medium, or large shirt. We are not talking about that. The medium is the thing that carries the wave pulses. So if I have a wave on a string, the medium would be the string. If I have a sound wave, the medium would be the air. If I have a water wave, the medium would be the water. Okay, so what you see shown here is a bunch of wave pulses. And on the upper one here, the medium is a thin, lightweight string. And then it comes to a boundary where it moves into a new medium. And the medium on this case is a thick, heavy rope. So when this wave pulse comes in, when it hits the medium, very interesting and very important things happen. Okay. What happens is that it's kind of like hitting a wall, and you are going to get some reflection. Okay, so this is the incoming wave, and this is before reflection, this is after reflection. Okay, so when this pulse hits the boundary, what's going to happen is some of the energy is going to be transmitted, and some of the energy is going to be reflected. And whether the reflected pulse is inverted or not inverted depends on if you're going from a medium where the wave velocity is high to a medium. So what is the velocity in the new medium? Is the velocity in the new medium higher, or is the velocity in the new medium lower? Okay, so the way it works is if you have a big heavy rope and this wave pulse comes along and hits it, well, the heavy rope has more mass. and that's going to slow things down. So the speed of the wave in the new medium is going to be slower than it was in the incoming thing. So in that case, that is going to behave very similarly to what we saw up here. That is like this upper case where the wave is hitting a fixed boundary. It's trying to pull the rope up, but because the rope on the right side is thicker and heavier, the rope is saying, no, I don't want to go up. And so that means that our reflected pulse is going to be lower. So if we go from string on the left side into rope on the right side, it behaves like this. But we might be the other way around. We might go from rope on the left side into string on the right side. In fact, let me just go back to this page here. Okay, so what we have here is we have the incoming pulse is in lightweight string, and then it hits this boundary where it goes to a heavy rope. So you'll see here that the reflected wave is inverted. Okay, and then some of it is transmitted. Now, it could be the other way around. Down here in part B here, the incoming wave is in a thick, heavy rope, and our boundary here is a transition to lightweight, thin string. And so that behaves like the case where you have the non-fixed boundary. So there will be some reflection, and notice the reflection here is not inverted. Okay. But notice that the transmitted wave is never inverted. That's important to note. So transmitted pulse is never inverted. But the reflected pulse, sometimes it's inverted and sometimes it's not, depending on whether you're going from light to heavy or heavy to light. So make sure that you memorize these rules here. So this picture that you see right here, might be a good idea to take a screenshot of it, although there is something in your book that's kind of corresponding to it. Okay. In tonight's homework, they'll ask you questions about it that you'll have to answer, even though you may not understand why it's important. But later, you will find out, especially when we talk about light waves traveling through glass, you'll find out that it's very important. In fact, tell you what, let's take a minute. Let's just talk about it right now. I want you to guys understand it. Okay, so let's assume that this is glass. And this is air, and this is air. So we have a light wave coming along and it hits here. So you guys know glass is transparent. So most of the light wave energy goes right through, but some is reflected. I mean, you guys have stood in front of a window and you know that you can see some reflection. It's not as good as if it was a mirror, but you do see some reflection. So some of the light here is reflected and some of it's transmitted. So if you're going from air into glass, that's like going from a string into a rope. So this light that's reflected will be inverted. Now, a lot of people don't realize that when the light comes out of the glass and goes back into the air again, you get another reflection at that point too. A lot of people don't realize that, okay? And so now, is this guy inverted or not? Well, if we're going from glass into air, that's like going from a heavy rope into a thin string. And so the reflected pulse in that case is not inverted. Okay. Now, you might think, why is that important? Well, the reason it's important is because this light ray that got inverted right there, it's going to come out here, and this light ray here is going to combine with this light ray right here. The two of them are going to combine together in very, very important ways, which is a good segue to what, okay, so what happens if you have two waves that are both laying on top of each other? How do they combine together? Okay, this is one of the most important concepts you're going to learn in physics, is what happens when you get light rays combining together? Well, they could either add together or they could cancel each other out. So let's take a look at condition A. And this is right straight from your, this one here is from your book. So in condition A, what we got is we got a pulse coming in from the left side, and we got a pulse coming in from the right side. Okay, so imagine that, imagine you got two people holding a rope, and the person on this side, they send a positive pulse. So they pluck the string and they pluck it upwards. And so they send a positive pulse racing down the rope. The person on the other side, at the same time that his friend plucks it, he's going to pluck it too, but he's going to pluck it downwards. Instead of plucking it upwards, he's plucking it downward. So we have what I like to call a positive pulse racing in from this side. We have a negative pulse racing in from this side. So let's go back to my drawing here. Okay. So let's say that this is time equals 1 millisecond after they have plucked it. Okay, this now is time equals 2 milliseconds after they plucked it. You can see that this pulse has now moved to the right. This pulse here has moved to the left, and the two pulses are now starting to interact with each other. The shape is slightly different than it would have been before because they're interacting with each other. The really interesting thing is what happens here at 3 milliseconds after they've plucked it. So the pulse from coming in from the right, this is where it would have been had the other pulse not been there. The pulse coming in from the left, this is where it would have been had the other pulse not been there. So the pulse from the right is trying to pull the rope up. The pulse from the left is trying to pull the rope down. So I'm sure you can see what's going to happen is they're going to cancel each other out. And so if I were to take a photograph at exactly that instant, I would see a flat rope. I would say, where did the pulses go? Okay. Now, if I take 1 millisecond later, so t equals 4 milliseconds now, this pulse that was coming from the left, it has now reappeared. And this pulse that was coming in from the right, it has now reappeared. So how can that be? Where did these guys come from? Well, if you go back to this instance right here, this photograph makes it look like the rope is not moving, but the rope is actually moving. I just happened to catch it right at the instant when everything was flat. But in fact, this part of the rope right here is moving downwards. This part of the rope is moving upwards. And so it's not surprising that a millisecond later, I'm going to have a downward pulse on this side and an upward pulse on this side. And then they're going to continue on in their merry ways. This guy is going to keep moving to the right. This guy is going to keep moving to the left. But the important thing is at the point where when the two of them both hit the same spot at the same time, they canceled each other out. And what we got is called destructive interference because they canceled each other out. Okay. What if the person on the left had put in a positive pulse and the person on the right had also put in a positive pulse? Well, you can see here what's going to happen. So when we get to 3 milliseconds here, when the two pulses are overlapping, then what's going to happen is the rope is going to get pulled up twice as high as it would have gotten pulled had there only been one pulse. So what's happening is what we call constructive interference, the opposite of destructive interference, okay? And so what happens is the rope gets pulled up twice as high as it would have gotten than before. Now, these letters A and N, these are important, okay? The N stands for node, and the A stands for anti-node. Node means that the two waves have canceled each other out. So that's the spot where the rope does not ever go up or down. Antinode is the opposite of that. That's where the two waves are working together to pull the rope up twice as high as it would have gone had it been only one pulse acting on it all by itself. So node and antinode are words that you guys need to know. All right, now the third case here, case C, is what do you have if the pulse coming in from the left is bigger than the pulse coming in from the right? Okay, so in this case, when the two of them get to, I'm sorry, I had to pause there because I had to smirk at what Taituan just wrote into the chat box there. Yes, he already knowed the answer here. Okay, so if we got the two pulses hitting at the same spot, but the pulse from the left is bigger than the pulse on the right, well, what's going to happen is what we call partially destructive interference. Okay, so we don't really have a true node, but it's not completely destructive, but it's partially destructive. Okay, so these are the three possibilities. So when two waves hit at the same time, you could either have destructive interference, or you could have constructive interference, or if the amplitudes of the two wave pulses is different, then what you're going to have is you're going to have partial destructive interference. Okay. All right, so now let's see what happens if we have our simulation set. So let's go back to that simulator that we were playing with a few minutes ago. Okay. So what I'm going to do now is I'm going to reset this. But instead of me giving the pulses, I'm going to turn on oscillate mode. So what we got now is it's connected up to a motor. And so you see, I'm sending a pulse and then following that by another pulse and then another pulse. So I'm sending a whole bunch of pulses. Those pulses are all hitting the opposite side and they're bouncing back. So I've got pulses traveling this way, and I've also got pulses traveling that way. And this pulse and that pulse are interfering with each other. And now also we've got damping here, which is kind of confusing things. I purposely put this on canvas because I want you guys to play with all these different settings. I'm going to turn off the damping. Let's see what happens if so what is damping? So if I turn the damping up, you can see what happens is that the rope is so heavy that the pulses, they all just get damped out before I get the other side. Let me turn the damping completely off and let's see if anything interesting happens. Not really noticing any patterns. Okay. Now, I want you guys to play with this, and I've even suggested some settings that I want you to use. So I want you to play with all of the settings, have them be whatever your heart desires, but make sure that one of the settings that you try is this one. So I want you to set it for oscillated with a fixed end with no damping and the highest tension. Okay, so we got fixed end, oscillate, highest tension, no damping. Okay, we're good. And then once we got that, now I want to set the frequency to 0.83 hertz. So what is it that's important about 0.83? Well, let's find out. Okay, so let's set the frequency down to 0.83 hertz. And let's restart it. Okay, watch what happens. Okay, so there's the pulse, there's the reflected pulse. And oh my goodness, look, the pulses are getting bigger and bigger and bigger. It's going crazy. If this was the Tacoma's Narrows Bridge, I would think that our bridge would be collapsing right about now. What is happening is we've got resonance. So the frequency that we are disturbing this string at just happens to match the natural frequency that it likes to vibrate at. So it's gone into a mode that we call resonance. And so, like I say, if this was the Tacoma Narrows Bridge, the bridge would be collapsing right now. Okay, so let me stop it for a second. What if we go up here by just a little bit? Instead of 0.83, let's take it up to 0.9. Now, that's not very much of a difference, right? Let's see what happens. Okay, so there's our first one. They're bouncing back. You can see they're getting a little bit bigger, but they're not going crazy. They're not resonating. And in fact, as time goes on, look, they're getting smaller. The amplitudes are getting smaller. Now it goes back to like 0 again. Okay, now they're getting bigger again. Okay, oops, now it looks like they've reached their maximum, but they're not going crazy like they were before. And now they're starting to get smaller again, smaller still. Whoops, okay, now they're going. So we're going through this really weird cycle, but at no point does it go crazy. It's not resonating. It will only resonate if the frequency is a magic frequency. And it's not really magic, okay? And so now let's go back up here again. So you'll notice that I said, okay, so I say, let's keep increasing the frequency till we get to 1.25 hertz. Let's see what happens there. Okay, so let's reset this. And let's take this up to 1.25. Okay, let's start the simulation. It's looking good so far. Whoops, they're getting bigger, bigger still. Holy cow, look, they're getting bigger and bigger and bigger. They're resonating again. Okay, we've got another Tacoma Narrows Bridge situation going on. Okay, so the thing is going crazy. So there's something magical about these two frequencies, right? So let me slow the motion down here. And then I'm going to stop it right there. Whoops, that's not a good one. Let's stop it there. Okay, that's pretty good. All right, so we have resonance. We have what's called a standing wave. And I propose to you that we can now look at this picture, actually, especially if we get out a ruler. If we pull out a ruler here, if we measure the distance from one trough to the next trough, okay, we can figure out what we need to where we can learn everything we need to learn about this wave. So when I say everything we need to learn, I mean frequency and wavelength. So in this case, the wavelength is from here to there. So it looks like the wavelength is about maybe 5.2 centimeters, which hopefully you guys know we shouldn't be working in centimeters. So let's write it as 0.052 meters. Okay, and the frequency is 1.25, whatever units we measure frequency in, which hopefully you guys now know is hertz, which is the same thing as 1/seconds. So if I wanted to know what is the wave speed, we could do this. And guess what? In your homework, that's what they're gonna do. Okay, so can you guys take a minute and calculate what the wave speed is? I'm gonna sit here quietly. I want you to calculate what is the speed of this wave. And I want you to type it into the chat box in a private message. I don't want other people to be able to see what you type. What do you calculate? So what we got is we got pulses here that are traveling to the right, and we got pulses here that are traveling to the left, and they're all traveling at a speed v. And so by knowing this information right here, we should be able to calculate what is the speed of those waves. Okay, I'm starting to see a couple answers now, but I need to see more. Good. Keep going. I want a couple more people here. All right. Okay, it looks like everybody's in agreement now that you're claiming that the speed of the wave is 0.065. So Austin, you were the first one to type it in. Can you just tell us, how did you figure that out?
It's the frequency times the wavelength from the equation, if you like rearrange it.
Okay, so when he talks about the equation, he's talking about lambda equals f over v. This is going to be your best friend for the rest of the year. This is going to be the most important equation you're going to use for the rest of the year. So it sounds to me like what he did was he rearranged this to solve for v. So he swapped places with the lambda and the v. So, oops, wait a minute. That's wrong equation. Oh, that's embarrassing. That's not the right equation. Lambda equals V over F. That's the right equation. If you guys had caught me on that, I would have to wear the wig right now. I haven't worn the wig for many, many weeks. That's a classic wig mistake. Okay, so let's multiply both sides by F. So what we get then is V equals F times lambda. And when you put in the numbers, you get V equals 0.65. Okay, now, is that V going to change? If I were to change the frequency, so let's say that I change the frequency back to 0.83. Okay, so let's do that. Take it back to 0.83. Okay, so what do you think? Is the speed of the wave pulse going to change? Now, a lot of people, and in fact, most people, if I were to ask you to vote whether the speed of the wave changes when I change the frequency, most people would say yes. But remember, the speed of a wave is only dependent on properties of the medium. The frequency is not a property of the medium. The only thing that affects the wave speed is the properties of the medium. So the thickness of the rope, how much mass the rope has and how tightly the rope is stretched, those would be things. So tell you what, let's recalculate our wave speed. Let's go back, let's reset everything with our new frequency. Let's go back and start it going, and let's get rid of the slow motion, go back to normal motion. Okay, so it's starting to oscillate wildly. Okay, so it's gone into resonance. Okay, so our bridge is now falling down. So let me put it back into slow motion, and then let me stop it right there. Okay, good. Okay, so let's see what is our wavelength. So our wavelength now looks like it's about 7.2 maybe. So our wavelength now, oops, turn on annotation here. So the wavelength now is approximately 7.2 centimeters, so 0.072 meters. Our frequency is now 0.83 hertz. Let's recalculate what is our wave speed. Okay, so remember that lambda equals V over F, so V then is equal to F times lambda. So let's take that times that, and let's see if we get a different number than we did before. So I get 0.072 times 0.83, and I'm getting a number that's very close. I mean, it's not exactly, but it's about 0.06, which is pretty close to what we got before. Now, why is it not exactly what we got before? Because of measurement error. Okay, so when I was measuring the wavelength here, it was hard for me to measure this node here because this node isn't really a true node. It's going up and down. So a little bit of measurement error. So basically, to within measurement error, the wave speed is the same now as it was before. Okay, so in your homework tonight, they're going to give you problems like that. They're going to have what's called a standing wave. Now, the best way to really get a feel for standing wave is to look at a video that I've posted on Canvas here. So if you go back into Canvas and go into the modules, and then let's scroll down to the very, very bottom. Here's a nifty little video that I don't have time to really play the whole thing for you. I want you guys to watch this video on your own, but let me at least play parts of it. Okay, so, and let me make it full screen. And let me skip.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave.
Okay, so let's see, let me get rid of that. Okay, so what he's done is he just turned the knob until he just happens by chance to reach the magic frequency where the waves traveling to left to right and the waves traveling right to left, they now interfere with each other in a way that is very important for you guys to know. So this is called a standing wave. And so this is a node, this is a node, and this is a node. So those guys are all nodes, okay? And then this and this, these are the anti-nodes, okay? And so this is a standing wave. In your homework tonight, they're going to ask you lots of questions about standing waves. So the idea is that the waves that are traveling to the left to right are interfering with the waves that travel right to left. And they're interfering in such a way that at this point right here, they always cancel each other out. You always get destructive interference at that point right there. And you always get constructive interference at that point right there. Okay, so this is called a standing wave. Now, what happens if we go to a different frequency? So up here, let me skip around. So watch the video, please. It's really good. And okay, so here. Okay, so he's changed the frequency. Now the wave speed is still the same because the wave speed only depends on properties of the medium. But what he's done here is he's changed the frequency. And so now you see we have two nodes in the middle, whereas previously we only had one node in the middle, all because he changed the frequency. So I'm not going to spend more time on this video, but I want you guys to watch that video from beginning to end. It's very, very important. And it will help you to understand your homework tonight. Okay, speaking of homework, let's talk about that. So this, by the way, you know, here's an example of that from the book of different standing waves. So make sure you read the book. In the book, they're also going to talk about reflections of waves when they hit boundaries. I don't have time to go into that. Just read the book. I think the book does a pretty good job of describing that. Okay, so here's your homework. So I want you to finish reading everything in chapter 14. Read the entire chapter. Do problems 27 through 30. And then you know how at the end of each chapter, they have a bunch of additional practice problems. So I want you to go and do those. Problems 68, 73, 83, 94, and 100. Right, so that will be due next time we meet. Are there any questions? Okay, well, just in case you have a question that you didn't want to ask because it was being recorded, I'll go ahead and turn off the recording so you can ask your question without embarrassment. If you don't have any questions, then I'm okay with you saying goodbye and see you guys later. Okay, so here goes the recording being turned off.